In the last video, we saw how to deal with open systems. There are many common steady flow scenarios that we see in the real world. Today, we're going to specifically apply what we did in the last video to some of these situations. Remember that in steady flow systems, nothing is changing with respect to time. Some systems that this can be applied to include nozzles, turbines, compressors, and mixing chambers, and a lot of other systems. Today, we will see how these systems work and how to analyze the thermodynamics of these systems. The first situation to be analyzed are nozzles and diffusers. These are basically the same thing. A diffuser is just a backwards nozzle and vice versa. Due to the constricting geometry of a nozzle, the flow speed will increase while the fluid pressure decreases. The opposite happens in a diffuser. Both diffusers and nozzles typically involve zero or very little heat transfer, work, or changes in potential energy. Therefore, these terms can all be neglected. Delta PE, Q, and W will all be zero. However, due to the changing velocity, there is generally a significant change in kinetic energy. Turbines and compressors are also basically the same thing. Just like the previous case, they are essentially the opposite of each other, or each other backwards. A turbine takes energy out of the fluid, while a compressor puts energy back into the fluid. This is also true for fans and pumps. For these components, the heat transfer is usually negligible, and there are no changes in potential energy. Sometimes the change in kinetic energy is important, but this is not always the case. The most important forms of energy in the analysis of turbines and compressors are the work, either into the compressor or shaft work out of the turbine, as well as the change in enthalpy of the fluid. The next component to be analyzed is a throttling valve. These are any kind of device that causes a large reduction in pressure of the fluid in the pipe. There's also commonly a temperature drop in these scenarios. However, this temperature change is generally too small to have any significant heat transfer. So for the thermodynamic analysis, we can usually neglect any heat. There is no work involved. There is no change in potential energy, and the change in kinetic energy is usually small as well. This then reduces to simply that the enthalpy on each side of the valve is the same. Next up, we have mixing chambers. This is where any two fluid streams come together. Here, the analysis can usually neglect any heat, work, or changes in both potential and kinetic energies, just like the previous case. One thing to take into account, though, are the mass flow rates of each stream. So in addition to conservation of energy, conservation of mass must also be satisfied. Conservation of energy then reduces to this equation down here, showing the rate of enthalpy addition from each individual stream equals the outgoing rate of enthalpy. Heat exchangers are involved in many types of systems. They are useful when there are two streams of fluid that have the opposite temperature requirements, one hot, one cold, and they can exchange energy between them. These have negligible work and changes in potential and kinetic energies. The heat transfer into the entire heat exchanger is also usually zero. They're usually insulated from the surroundings. However, there is heat exchange between the two streams of fluid. Therefore, this heat exchange is equal but opposite between each fluid, and conservation of energy can be applied to each fluid independently. Last up, we have pipe and duct flow. This situation is a lot more case dependent than the others we have seen. There may or may not be significant heat and/or work addition. Similarly, there may or may not be significant potential and/or kinetic energy changes. So in terms of conservation of energy, you have a lot more responsibility to determine which terms need to be included and which can be excluded. So those are some of the common examples that you may encounter in the real world. We will go through the analysis and see many examples of these scenarios in class. Until then, here is your pre-lecture example to work on, as well as the answer. Have fun.